In this video, we'll be going through the Level 2 Electricity and Electromagnetism exam. Question 1. In a first-class cabin, the seats are fitted with 4 heating units, 2 for the hands and 2 for the feet. The hand units have a resistance of 6 ohms and the foot units 10 ohms. The heating circuit is connected to the 28-volt supply. Question A asks us to show the combined resistance of the hand units is 3 ohms. And so in this case we of course have 2 resistors in parallel, which means we need to use this equation here, which states that the 1 over our total resistance is the sum of the 1 over resistances. In this case, our 1 over total resistance is 1 over our 6 ohms here, plus 1 over our 6 ohms here. To solve this equation, we can flip both sides, which indeed gives us 3 ohms. Question B. Calculate the current flowing through the ammeter. And given the position of our ammeter here, the current in question is the total current in the circuit. And so knowing the equation V equals IR, Ohm's law, we know that the current is V over R, which means that the total current in the circuit is going to equal the total voltage in the circuit divided by the total resistance in the circuit. Now our voltage, we already know our voltage is our 28 volts, but we don't know our total resistance. What we found in the previous question is the resistance of this section here, which was 3 ohms. In order to find the total resistance of the entire circuit, we're going to need to do the same thing to our foot units here, and then add that resistance to our 3 ohms. So let's do that. So our total resistance is our 3 ohms we found in the previous question, plus the total resistance of this foot unit section, which we can find using the same equation here, but instead of the 6's, we're going to use our 10's. And that gives me a total resistance of 8 ohms. Putting our numbers into our equation over here gives me 3.5 amps. One of the foot units stops working. Explain what effect this would have on the current through a single hand unit. So our 10 ohm resistor here has stopped working, which means that all of the current is now going to flow through here. Now, because we only have one pathway instead of 2, that means it's going to be harder for the current to flow through the circuit, which means that the resistance will increase. I know it's a little bit counterintuitive that you're taking away a resistor and the resistance increases, but you need to think of it in terms of removing a pathway. You've removed a pathway for the current to flow, and so it's going to be more difficult because there's more congestion. So let me put that into words. The total resistance increases as the current has less paths to travel. This causes less current to flow in the circuit and therefore less through each hand unit. As an upgrade, the airline adds an additional heating unit, labelled R, to the seat. When the new heating unit is added, the power output from the supply is 120 watts. What is the value of the resistance R of the new heating unit? So let's break down what we know. We know that the total voltage in the circuit is our 28 volts. We know that the power consumed by the circuit is 120 watts. And since P is equal to IV, that means that our total current in the circuit is our power divided by our total voltage, which gives me 4.30 amps to 3 significant figures. The easiest way I see to approach this problem is to start with Ohm's law and apply it to the entire circuit, so let's start by doing that. Now, we know the total voltage, we know the total current. The total resistance is something we're going to need to break down. Now that's made easier by the fact that in question 1 we found that the total resistance of the hand units was 3 ohms. And by now we're all very much familiar with adding resistors in parallel, so hopefully you're comfortable with me writing this. What we end up with is an equation that we need to solve for R, which is going to be a little bit of a pain in the backside, but we'll break it down step by step. Firstly, I'm going to divide both sides by IT. Next, I'm going to subtract 3 from both sides. Now I'm going to take the inverse of both sides, or in other words, I'm going to flip both sides. Next, I'm going to subtract our 1/10s from both sides. And lastly, I'm going to flip both sides to bring our R into the numerator. I'm also going to swap the sides of the equation so I have R on the left side. Putting our numbers in, which gives me 11.7968. Since the question gives us 2 significant figures, we're going to round it to 2 significant figures, which gives us 12 ohms. Question 2. Lightning is typically caused by a buildup of electrons in clouds being released to Earth. The bottom of the cloud is negatively charged and the ground under the cloud becomes positively charged. The cloud and the ground can be modelled by a pair of parallel plates. The voltage difference between a particular cloud and the ground is 1.75 times 10 to the 8 volts, and the electric field strength is 8.57 times 10 to the 4 volts per meter. Find the height of the cloud above the ground. So the quantities that we are given is our voltage and our electric field strength. What we're trying to find is our height, which is given the symbol D. The equation that we need to use is right at the top of your formula sheet, and that is that the electric field strength is equal to the voltage divided by our distance. Rearranging that for distance, and putting our numbers in, which gives me 2042, rounding that to 3 significant figures, because that's what we're given in the question, gives us 2040 meters. The weather balloon is released from the ground. The balloon has a charge of 3.7 microcoulombs, which they've kindly written out in full here. Calculate the size and direction of the electrostatic force exerted on the balloon when it is halfway between the cloud and the ground. And so here we're given our charge, and knowing our electric field, we can use the equation that force is equal to our electric field times our charge. We know the electric field from up here. Now, they've kind of tried to trap you by saying halfway. They're trying to tempt you into overthinking the problem. Now, if we were to draw the electric field lines in this scenario, they would look something like that. And what you might notice is that they don't get closer together or further away when they move from the base of the cloud to the ground. Because they don't get closer together or further apart, that means that the electric field strength is the same throughout the entire distance here. The electric field strength is going to be the same here, as it is here, as it is here, as it is here. Okay, so the electric field strength is just this, no matter where you are. So let's put those numbers in. Which gives me 0.317. Because we're given 3 significant figures, we'll round that to 3 significant figures, which gives us 0.320 newtons. How does the electrostatic force on an electron change as it travels from the cloud to the ground? Use physics principles to explain your answer. And so this is pretty much what I was explaining before. We see that the force on our charge is F equals EQ. The electric field does not change no matter how further you are from the base of the cloud compared with the ground. It is the same no matter where you are. The charge on the electron is not going to change either, and so we wouldn't expect the force to change. So let's explain that. F equals EQ. Since the electric field strength does not change between 2 parallel plates and the charge on the electron is constant, the force will not change. An electron is discharged downwards from the base of the cloud with a speed of 1.20 times 10 to the 5 meters per second. It reaches a speed of 4.20 times 10 to the 5 meters per second. Calculate the distance it could have travelled from the cloud to have reached this speed. So let's write down what we know. Well, we know that this here is our initial velocity, and that this here is our final velocity. We know the electric field strength from earlier. And we know the mass and the charge of our electrons, which are given at the top here. Now, given that we're given velocities, that implies that we will have to think about kinetic energy. And so if we're going to look from a lens of kinetic energy, we're going to be interested in the transformation of this kinetic energy from the electric potential energy. Now, the equation on your formula sheet for electric potential energy is this here. Solving that for the distance that we need. Where we know our electric field, we know our charge, but we don't know the change in potential energy. So we need to find that somehow. The way that we can do that is by recognizing that the change in our electric potential energy is going to be our final kinetic energy minus our initial kinetic energy. And so let's just pause a moment to think what's happening. So we have our cloud and we have our ground. And so the electron is moving from the cloud to the ground. As it does so, it is gaining kinetic energy. It is going from a speed of 1.20 to 4.20 times 10 to the 5. It gains that kinetic energy by losing electric potential energy. And that's what we're describing with this equation here. Now we know that kinetic energy is half mv squared from our formula sheet. Doing a little bit of factorizing to make this easier to type into the calculator, I'm going to take the half and the m out front. And it's in this step you should hopefully see that one of the pitfalls of this question is taking the difference in the velocities. If you took the difference in the velocities, you're going to get the wrong answer. And the reason is we're looking for the difference in the kinetic energy, and the kinetic energies have velocity squared. So if you take the difference in the velocities, you will get the wrong answer. You have to specifically find the difference in the kinetic energies, taking into account that it's the difference in the velocities squared. So let's put those numbers in. Which gives me 7.38 times 10 to the minus 20 joules. Now putting our numbers in on this side, which gives me negative 5.38 times 10 to the minus 6 meters. Question 3. A plane with metal wings has one wingtip painted blue and the other wingtip red. The wingspan is 68.4 meters. The plane is flying horizontally at 850 kilometers per hour, which they've kindly given to us in meters per second, in a region where the Earth's magnetic field is vertical and has a strength of 40 microteslas, or 40 times 10 to the minus 6 teslas. And we're given a handy diagram down below. Question A asks us to show the voltage induced between the ends of the wings is 0.646 volts. And so essentially what this question is doing is modeling the wingspan of the plane as a wire in a magnetic field. The voltage for a wire moving in a magnetic field is given by this equation here, where we have our magnetic field strength B, we have our velocity v, and we have our length L. Putting our numbers in, gives me 0.645696, or rounding to 3 significant figures, which is what the question gives us. We indeed get 0.646 volts. Complete the following table. Assume each change is made to the original plane separately. So if the speed of the plane increases, the effect on the size of the induced voltage is that it's going to go up. We can see in this equation here that if the speed increases, then our voltage must also increase. If the plane is flown in the opposite direction at the same speed, the size of our induced voltage will not change. And if the plane climbs vertically upwards from the Earth, which I'm not sure how realistic that scenario is, because the velocity of the plane is in the same direction as the field lines, we're going to see no voltage induced. You might recall that the maximum effect takes place when the velocity and the field are at right angles, 90 degrees, and you get no effect if they're at 0 degrees, or parallel, or in the same direction, in other words. For our other column, which color wingtip is positive? So let's work that out in our original scenario. So we're going to need to use our right hand slap rule. So you're going to have to follow along at home. If you point your fingers in the direction of the magnetic field, which is into the page, point your thumb in the direction of our plane / our wire, which is towards the right, your palm is going to be pointing up the page in this direction here. So that is the force on our positive charge, which means our positive end is going to be the red and our negative end is going to be the blue. Now, increasing the speed of the plane is not going to change this, so our wingtip color is still going to be red. Flying the plane in the opposite direction at the same speed. Now, this strikes me as a bit of a trick question, because if the plane is flying in the other direction, now bear with me while I draw a plane flying in the other direction. Magnificent if I don't say so myself. So if the plane is going in the opposite direction, we will expect that the force on the positive charges is going to be in the opposite direction as well. But because the plane has turned around, the red is now on the bottom, which means that the positive end is still going to be the red tip. And if the plane climbs vertically upwards from the Earth, well, we're going to have no voltage at all, so neither, I guess. Inside the plane, an electrical feeder wire runs under the floor of the cabin, and so we're given a diagram here. The wire is connected to a 20-volt supply. We're given that the length of the wire is 5.9 meters, and the circuit has a 5 ohm resistance. If the current is flowing in the direction shown in the wire, calculate the magnitude and state the direction of the force on the wire due to Earth's magnetic field. So first of all, let's find the magnitude. Now, the equation for the force on a wire in a magnetic field is this one here. Where we know our magnetic field, we're given that earlier, we know the length of the wire, we're given that as 5.9 meters. We don't know the current though, so let's find that. Now, although we don't know what the current is, we do know what the voltage is, and we do know what the resistance is. We know that V equals IR, which means that I is equal to V over R. Putting in our numbers, which gives me 5.6 amps. Plugging that into our equation over here, which gives me 1.3216. Since the equation gives us two significant figures, we write that as 1.3 times 10 to the minus 3 newtons. As for the direction, we're once again going to need our right hands, and you'll need to follow along at home. Point your fingers in the direction of the field, which is into the page. Point your thumb in the direction of the current, which is upwards, and you'll find that your palm is pointing towards the left. Question D. An engineer designs a speed warning device that consists of a wire connecting the wing tips and a 0.5 volt lamp. The engineer states that the faster the plane goes, the brighter the lamp will glow. Use physics principles to explain and justify if and how this arrangement would work as a speed warning device. And so we've already used the right hand rule on this scenario. If you point your fingers into the page, your thumb towards the right, the direction of the plane's velocity and the wire's velocity, you'll see that the force on our positive charges is going to be upwards, which means that the top here is going to become positive and the bottom here is going to become negative. The magnitude of that voltage induced is given by the equation V equals BVL. The problem is, this is not a complete circuit, so that when the voltage is induced, this end will get positive, this end will get negative, and current will cease to flow. And so the crux of this question is that you are going to get a voltage induced in the wire, but you aren't going to get a current. So let's put that into words. As the plane moves through the field, a voltage will be induced in the wire. Via V equals BVL, we see that the greater the velocity, the greater the voltage. Via the right-hand rule, we see that the red end is positive and the blue negative. As the wire does not form a circuit, however, no current will flow and the bulb will not glow. This would not function as a speed warning device. And that's it.